Colligative properties are properties whose value depends only on the number of solute particles in a solution, in other words, on the concentration of the solution, and not really on what the particles are. One example of a colligative property is demonstrated by vapor pressure of solutions. The vapor pressure of a solvent above a solution is lower than the vapor pressure of the pure solvent because the solute particles replace some of the solvent molecules at the surface. So the addition of a non-volatile solute reduces the rate of vaporization and decreases the vapor pressure because, think about it, the solute particles are going to be taking up some space at the surface, and they're going to be decreasing the amount of solvent particles that can enter the vapor phase. So when you have a solution versus a pure solvent, an equilibrium is established just like with the pure solvent giving the vapor pressure, but the vapor pressure will actually be lower for the solution relative to the pure solvent. Just like a concentrated solution will draw solvent molecules toward it due to the natural drive for materials in nature to mix, a concentrated solution will also draw pure solvent vapor into it due to this same tendency to mix, and this results in a reduction in vapor pressure. Let's consider a situation where we have two beakers under a bell jar. We have a pure solvent on the left and a concentrated solution on the right. Initially, both of these begin to vaporize, and the pure solvent enters the vapor phase, and so does the solvent from the concentrated solution. Over time, the level of the pure solvent drops and the level of the solution will rise relative to it, even though they may have had the same amount initially. So what happens is, because the concentrated solution has a tendency to draw solvent particles toward it, just like what we saw with the seawater, the level of the solution at equilibrium will be higher than the level of the pure solvent, even though they were equal initially, due to nature's tendency toward mixing. We'll apply this information with Raoult's law, which states that the vapor pressure in solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. What's the vapor pressure of a solution in which the mole fraction of the solute is 0.2 and the vapor pressure of the pure solvent is 100? Assuming a single non-volatile, non-electrolyte solute. Well, remember, the total mole fraction has to equal to 1. So if the mole fraction of the solute is 0.2, then the mole fraction of the solvent is 0.8. Okay? And so 0.8 times 100 would give us 80 torr. The difference between the vapor pressure of the pure solvent and the vapor pressure of the solvent in solution is called vapor pressure lowering, and that change in vapor pressure is given by the vapor pressure of the pure solvent minus the vapor pressure of the solution, and that difference is equal to the mole fraction of the solute times the vapor pressure of the pure solvent. Previously, we were discussing non-volatile solutes. But if you have a volatile solute, you have to consider the vapor pressure contributed by both of them. The total vapor pressure is equal to the vapor pressure of the solute plus the vapor pressure of the solvent. And the vapor pressure of the solute will be equal to the mole fraction of the solute times the partial pressure of the pure solute. And the vapor pressure of the solvent is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. Ideal solutions follow this law, but we can have deviations from this law if the solute-solvent interactions are stronger or weaker than an ideal solution. So when the solute-solvent interactions are stronger than the solute and solvent-solvent interactions, the total vapor pressure of the solution will be lowered. If the solute-solvent interactions are weaker than the solute-solute and solvent-solvent interactions, the total vapor pressure of the solution will be greater. These charts demonstrate deviations from Raoult's law. On the left, we have an ideal solution demonstrated. Here we have the vapor pressure of pure B, and here we have the vapor pressure of pure A. As the vapor pressure of pure A increases, we see that the partial pressure of B decreases and the partial pressure of A increases. And we have a linear relationship. If we have stronger solute-solvent interactions, we have a negative deviation from Raoult's law. As the vapor pressure of A increases, we see this negative deviation in the total vapor pressure of the solution because the vapor pressure is lower than what would be anticipated due to these stronger interactions. If we have weaker solute-solvent interactions, we get positive deviations from Raoult's law. Here we see the vapor pressure of solution is greater than we would expect due to these weaker solute-solvent interactions. When a solute is dissolved in a solvent, the vapor pressure lowering occurs at all temperatures. This results in the temperature required to boil the solution being higher than the boiling point of the pure solvent, and the temperature required to freeze the solution being lower than the freezing point of the pure solvent. Let's say a solution contains equal amounts of liquids, component A and B. The vapor pressure of pure A is 100 millimeters of mercury, and that of pure B is 200. The experimentally measured vapor pressure of the solution is 120. What are the relative strengths of the solute-solute, solute-solvent, and solvent-solvent interactions in the solution? Well, let's think about this. The pressure for the solute for an ideal solution would be the mole fraction of the solute times the vapor pressure of the pure solute. And this is a liquid solute. And that would be 0.5 times 100, which would be 50. The vapor pressure of the pure solvent is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. And remember, everything equals to 1, and we have half of one in the other, so the mole fraction is 0.5 times the vapor pressure, which is 200, so the vapor pressure due to the solvent is 100. So if we add those together, we would expect a vapor pressure of 150, but this is lower. So that means that we have stronger interactions between these two components. When a solution exists, the freezing point is depressed relative to the pure solvent, and the boiling point is elevated relative to the pure solvent. The change in freezing point is given by delta T sub F. And this is the freezing point of the solvent minus the freezing point of the solution. And this can be calculated as the mole concentration times K sub F. And this freezing point depression constant K sub F depends on the solvent. And we saw a chart earlier listing those freezing point depression constants. The units of K sub F are degrees C per mole. The boiling point elevation is calculated similarly. The boiling point of a solution minus the boiling point of the pure solvent is given by delta T sub B. That's the change in boiling point. And it can be calculated as the mole concentration of the solution times K sub B for that solvent. We see here in this chart different K sub F and K sub B values for various solvents. So the K sub F and the K sub B are listed here on the right, and you see along with that the normal boiling points. Let's consider a situation where solution A is a 1 mole solution with a non-ionic solute and water as the solvent, and solution B is a 1 mole solution with the same non-ionic solute and ethanol as the solvent. Which solution would have the greater increase in its boiling point relative to the pure solvent? We see here that the Kb for ethanol is 1.22 degrees C per mole versus the Kb for water is 0.512. So if we had the same concentration, we'd have a greater effect for the ethanol. So solution B would have the greater increase in its boiling point.